Number 1, factor the expression 125x cubed minus 27 completely. So hopefully you look at this and recognize that this has the structure of the difference of perfect cubes. So this is something cubed minus something else cubed. Well, what cubed gives me 125x cubed? Well, 5 cubed is 125, and x cubed is x cubed. What cubed is 27? Well, 3 cubed is 27. So when I factor this, the linear term is easy. 5x minus 3, same sign, 5x minus 3, times the first thing squared, opposite sign, so plus the product of them, plus 5x times 3 is 15x. Always positive, the last thing squared is 3 squared, which is 9. So we have 5x minus 3 times, well, what's 5x squared? 5x times 5x is 25x squared, plus 15x plus 9. The most common mistake was people writing 5x squared there instead of 25x. That is not okay, because those are not equivalent. So, factored completely, that's how that difference of perfect cubes factors. Write this in quotient remainder form. So write this quotient in quotient remainder form. I'll do reverse tabular. If you're a long divider, you're going to use the same process. 2x plus 3. Notice that you're going to need some kind of placeholder. You're going to need a 0x squared term, regardless of which way you do this. I know I need a 4x cubed there. What times 2x is 4x cubed? Well, 2x squared. Multiply through. 2x squared times 3 is 6x squared. I want 0 of them. I don't want any x squareds there, so that has to be a minus 6x squared there. Negative 3x times 2x is negative 6x squared, and I can multiply through. Negative 9x. I have negative 9x, I want 5x. So I'm going to need to add, how many? I'm going to need to add 14. I'm going to need to add 14 there. 14x. 14x minus 9x is 5x. And I get 7 times 2x is 14x. 7 times 3 is 21. But I want to get out 10. I only want 10 in there. So I have a remainder of negative 11. Because 21 minus 11 gives me 10. So in quotient remainder form, that quotient is 2x squared minus 3x plus 7 minus 11, that's the negative 11, over my divisor of 2x plus 3. How could you check that this is right? Well, you could plug in negative 3 halves, because that's when the denominator would be 0. Plug that in to 4x cubed plus 5x plus 10, and that'll give you a remainder of negative 11. If I plug in negative 3 halves into there, I'll get my remainder of negative 11. That's the remainder theorem at work there. 3. Algebraically prove that x cubed plus 9 divided by x cubed plus 8 equals 1 plus 1 over x cubed plus 8, where x is not equal to negative 2. We throw out x equals negative 2 because if you plug it in, you'll divide by 0. So I need to start with one side and make it look like the other. I'll start with this side. Factoring here wouldn't help because x cubed plus 9 is not a perfect cube. What you need to do is you need to divide somehow, whether that be with inspection or with long division. They look awfully similar, so I'm going to write this as x cubed plus 8 plus 1, because that's 9, over x cubed plus 8. All I did there was I took that 9 and I broke it apart. I'm going to distribute this division here. X cubed plus 8 over x cubed plus 8. I'm dividing those two. Plus 1 over x cubed plus 8. I'm just splitting apart that fraction. Well, x cubed plus 8 divided by x cubed plus 8 divides to 1. Plus 1 over x cubed plus 8. So I took this side and I made it look like that other side. So therefore I proved that those two are equivalent. You also could have started with this side and made it look like that side by getting a common denominator. Either way works. You could have also done long division. You need to somehow algebraically show that if I start with one side, I end up getting the other side. Number 4, use an appropriate procedure to show that x minus 4 is a factor of the function. Explain your answer. There are many ways to show that x minus 4 is a factor. There are many ways. I think the most efficient way is using the remainder theorem. The remainder theorem says find f of 4. F of 4 is the remainder when I divide. F of 4 is the remainder of when I divide by x minus 4. So f of 4 is 2 times 4 cubed minus 5 times 4 squared minus 11 times 4 minus 4. Hopefully, we get 0, because if I get 0, then it is my remainder. 2 times 64 minus 5 times 16 minus 44 minus 4. Hopefully you just type this all in your calculator at this point. 128 minus 50 minus 80 minus 80 minus 44 minus 4. So I have 128 minus 128, which is 0. So the remainder theorem tells me that when I divide by x minus 4, my remainder is 4. Or you could say, since 4 is a 0, because when I plugged in 4 I got 0, x minus 4 is a factor. You could have also divided and shown that there was a remainder of 0, but I think using the remainder theorem here is the clear and obvious way. So since 4 is a 0, x minus 4 is a factor. 5. If a, b, and c are all positive real numbers, which graph could represent the sketch of the graph of p of x equals negative a times x plus b times x squared minus 2cx plus c squared? So, some of you did this, and this was probably the best way to answer this question, was you picked numbers for a, b, and c, and then saw what the graph would look like on your calculator. I'm going to go through the algebraic way of doing this first, and then I'm going to plug in numbers, and you'll see that the graph looks like the correct answer. So, I notice that I have a negative leading coefficient. This is negative a is the leading coefficient, and I have x times x squared, so this is an x cubed polynomial. I don't know what else happens, but I know I have a negative leading coefficient and an x cubed polynomial. If you run through the dance in your head, this function looks something like that. So I know choices 3 and 4 are gone, because it has that type of end behavior. Another important part of polynomials are their zeros. What are the zeros of this polynomial? Well, I know x plus b equals 0, which means x equals negative b is a 0. So my polynomial should hit the x-axis at x equals negative b, which forces it to be choice 1. Notice that x squared minus 2xc plus c squared, what multiplies to c squared that adds to negative 2c? That's x minus c times x minus c. So that's really x minus c squared equals 0. So I have a 0 at x equals c of multiplicity 2. And notice that this graph here, I have a 0 at x equals c, and its multiplicity is 2, because it touches c and then turns back around. That's the proper algebraic way to do this one. You really didn't need to factor the quadratic there. You needed to recognize the leading coefficient was negative, so it had to be 1 or 2, and had a 0 at negative b. If you plugged in numbers like a equals 1, b equals 2, and c equals 3, and graph this on your calculator, if you graphed negative 1 times x plus 2 times x squared minus 6x plus 9, you would notice that this graph has the same structure as the graph represented here in choice A. This graph has the same structure as here in choice 1. So there are multiple ways to do this question. This is a trickier question though, because you needed to use end behavior and zeros of a polynomial. Number 6, if g of c equals 1 minus c squared and m of c equals c plus 1, then which statement is not true? The Regents exam loves these not true questions because you have to go through all of the work. What is g times m? What is g times m? So I need to do 1 minus c squared times c plus 1. The quickest way to do this is going to be to make a table. 1 minus c squared, c plus 1. 1 times c is c, minus c cubed, 1 minus c squared. So I have 1 plus c minus c squared minus c cubed. So choice 1 is correct. It drives me crazy that it's not written in standard form, but it will live. Choice 2. g plus m, so I need to add them together. What is g plus m? G plus m is 1 minus c squared plus c plus 1. That gives me 2 plus c minus c squared. Again, I have no idea why this is not in standard form, but that is true, so it's not the answer. What is m minus g? I'm doing m minus g, so c plus 1 minus, notice I need parentheses here, minus that quantity, c plus 1 minus 1 plus c squared. Those add to 0, so I get c plus c squared. Choice 3 is a true statement, so it is incorrect. So it means it has to be choice 4, and let's see why. m is c plus 1 over g is 1 minus c squared. We'll notice that the denominator factors as 1 plus c, 1 minus c. And c plus 1 and 1 plus c are the same thing here, the commutative property of addition. So we don't need to have a factor of -1 because the commutative property of addition says those are equivalent, so they divide to 1, not -1. So that's why choice 4 is incorrect. Number 7. The completely factored form of this polynomial is, just looking at my choices, and it drove me crazy that some of you picked choice 1. Choice 1 has d squared minus 9 in it. That is the difference of perfect squares, so it's not factored completely. It cannot be choice 1. I cross that out immediately. I have 4 terms here, so I have to do some kind of grouping. But before I group, I'm going to want to look for a GCF. 2, 6, 18, and 54, I can take out a 2, and I can also take out a factor of d. So I'm left with d cubed plus 3d squared minus 9d minus 27. You didn't have to do that, but it's going to make your grouping a lot easier. So I have 2d times, well, now I'm going to group. I can take out a d squared, and I'm left with d plus 3. I need to end up with a d plus 3, so what am I going to have to factor out? Factoring out a -9 will get me a d plus 3 there. So I have d plus 3, because that's my new GCF, and I'm going to factor out a d squared minus 9. And don't circle choice 1 because d squared minus 9 is the difference of perfect squares. So that's d plus 3, d minus 3. So I have 2 factors of d plus 3, which is why it's choice 3. It's 2d, d plus 3 quantity squared times d minus 3. Choice 3 is the correct answer. It's very tempting to pick choice 1, but you did all of that beautiful grouping to get it wrong. Don't forget the difference of perfect squares. Number 8, express this in simplest form. So this is a complex fraction, and we can't panic because it's a complex fraction. It's really 4x minus x squared over x squared plus 7x plus 12 divided by the denominator of 2x minus 4 over x plus 3. Well, I know how to divide two rational expressions. These are nice one whole fraction, so I can multiply by the reciprocal. Or I can keep change flip for you keep change flippers out there. Because it's written as one fraction, I can keep change flip. We need to keep in mind how to work with rational expressions. I do not need a common denominator to multiply. I just multiply across the top, multiply across the bottom. But before I do that, I want a factor. And 4 minus x squared factors like that do not go around changing the order because you want to. This is a trinomial whose leading coefficient is 1. So plus 3 plus 4, because that adds to 7 and multiplies to 12, times x plus 3 over, take out a factor of 2 there. So now I can start dividing if there's a common factor in the numerator and the denominator. X plus 3 divided by x plus 3 is 1, so we say goodbye, goodbye. And finally, I see 2 minus x and x minus 2. Those divide out, but leave behind a factor of -1. So I have -1 times 2 plus x over 2 times x plus 4. Any answer in simplest form, you could have distributed those in, you could have done something with those, but any answer where those are your only factors left in the numerator and denominator, that's in simplest form. So again, to deal with rational expressions, write it as the division, write it as a division statement, To divide, we multiply by the reciprocal. We keep change flip. Number 9. Number 9 is a monster of a question. Number 9 is a monster of a question, but it's all good stuff that we need to know. Given z of x, z of 2 is 35, and z of negative 5 is 0, algebraically determine the zeros of z of x. The first thing I notice when I look at z of x is there's that darn b there. So to figure out b is, I'm going to have to plug in one of these points. They give me 2 points here, I need to plug in one of them. It doesn't matter which one you pick, you're going to get the same b value. I like working with this one because it's equal to 0. So when I plug in a negative 5, when x equals negative 5, I get out a 0. So 0 equals 6 times negative 5 cubed plus b times negative 5 squared minus 52 times negative 5 plus 15. So I have 6 times negative 125 plus 25 squared, negative 5 squared is 25, so plus 25b plus 260 plus 15. 0 equals negative 600 negative 750 plus 25b plus 275. So when I add those together, I get 0 equals minus 475. Yes, because 475 plus 275 would give me 750. Plus 25b. I need to solve for b now, so I'm going to add that over. 475 equals 25b. Divide by b, and you get b equals 19. If you plugged in the other point, you also would have gotten 19. Your choice of which point you plug in. That was like the first third of the question. I know now the function I'm dealing with is z of x equals 6z cubed, 6x cubed plus 19x squared minus 52x plus 15. So maybe I can group this. And unfortunately, the answer is no, you can't group this. So to algebraically determine the zeros, I need to divide somehow. And this is the key thing. Negative 5 is a 0. Negative 5 is a 0, which means that x plus 5 is a factor. Because negative 5 gave me a 0, I know x plus 5 is a factor. So I need to divide. I need to divide that polynomial by x plus 5 to figure out the other factors. I'm going to do reverse tabular here to save some space. I got a 6x cubed from that term, so what times x is 6x cubed? 6x squared. Multiply through. So you needed to recognize that negative 5 was a 0, which means x plus 5 is a factor, and divide. I need 19x squared, and I have 30 of them currently, so I'm going to need negative 11 in that box. Well, negative 11. X times x is negative 11x squared. Negative 55x after I multiply through. I only want negative 52 of them, so I'm going to have to add 3 of them here. Plus 3. 3 times 5 is 15, so I have a remainder of 0, which is good because x plus 5 is the factor. Which tells me that z of x can be written as, notice, this is what's nice about reverse tabular, is you see that multiplication relationship there. X plus 5 times 6x squared minus 11x plus 3. I can rewrite z of x, this polynomial here, as the product of those two. Well, if I want to find the zeros, I need to factor it more. That's a quadratic with a leading coefficient, so I'm going to have to use the AC method. I'm going to come over here to the side. What multiplies to a times c? What multiplies to 18? That adds to negative 11. What two numbers multiply to 18 that add to negative 11? Negative 9 and negative 2. So I have 6x squared and minus 9x. I'm splitting up that middle term, minus 2x plus 3. Now I group it because it's 4 terms. Factor out a 3x from the first two and get 2x minus 3. I need a 2x minus 3, so I'm going to have to factor out a negative 1. So z of x is x plus 5 times 2x minus 3 was my GCF down there. Notice that I only have one of them. It's not squared. I just have one factor of that because that's my GCF times 3x minus 1. So, now that I factored it here, that's not my final answer. I need to find the zeros. So 0 equals x plus 5 times 2x minus 3 times 3x minus 1, and I can use the zero product property. X plus 5 equals 0, which tells me that x is negative 5. 2x minus 3 equals 0. I'm going to add 3. 2x equals 3, which tells me that x equals 3 halves after I divide. So negative 5 is a 0, 3 halves is a 0, or 3x minus 1 is 0. Add 1, 3x equals 1, divide by 3 and get x equals a third. So those are the three zeros of this polynomial z of x. This question was a monster. You had to first plug in a point to get the b value. If you're ever missing a value of a polynomial, plug in a point. You had to recognize that x minus 5, x equals negative 5 was a 0, which meant that x plus 5 was a factor. Well, if something's a factor, I can divide it in to figure out the other factors. The reverse tabular looks nice there because it saves me a lot of space, and I know I can multiply those two together to get my answer. This is a trinomial whose leading coefficient is bigger than 1, so I have to go through the entire AC method, which involves grouping.